Everyone, welcome back to another logic lesson online. Say that 3 times fast. So today we're going to be taking a look at the 3rd chapter of the formal logic primer. We're going to be looking at logical operators. So what we've already looked at previously, in chapter 1 we were looking at translation. So how to move from natural language, a language like English, into the sort of bite-sized chunks of information we need to work within statement logic. So what we try to do there is boil everything down to simple statements. So we try to take a natural language formulation, whatever the sentence might be, and break it down into the smallest little chunks it can be to wind up with the simple statements. Simple statements are the sort of thing that can be true or false on their own, and no part of it can be true or false, while some other part could have a different truth value, as we call it. So being true or being false is a truth value. Sentences, statements have truth values. Other things like commands and questions don't. So what we're trying to do effectively, this is the whole idea, is take information, break it down to the smallest piece that could be true or false, and do that with all the information we have. So rather than getting a whole bunch of information separately and getting confused in some sense about what's true and what's false and how it all fits together, what we're doing as we're moving into this artificial language that we're using, this symbolic language that we're working towards, we're going to make a pretty big step today towards actually being able to use it effectively, is take that whole universe of information, break it down into the smallest little pieces we can, separate them out, determine which of them are true and false, and that's where we really have to use Hughes and Lavery, as well as, just good thinking skills, good research skills, looking at evidence and so on, determining what reason we have to believe whether or not a simple statement is true or false. And then once we have all those little simple statements, we can say, well, okay, this is true and this is true, but that's false and this is false. We can see how they all fit together. Okay? That's what we're really doing. So we're in chapter 1 just trying to break things down to those little pieces. And this is really just the method of analysis. So when you think about analytic writing or analytic thinking, being able to analyze complex information, what does that mean? Well, break it down into tiny little pieces, right? Little pieces that we can manage, we can make sense of, we can think clearly about, and then see how all those little pieces connect to each other. In chapter 2, we were looking at truth tables. Just what they are, how we construct them, how we make them, how we read them, what they're showing us. But we couldn't finish dealing with truth tables, because part of what truth tables show us are, all truth tables show us are truth values. And for simple statements, that's very straightforward. Either a simple statement is true or it's false. Now, a complex statement is also either true or false, but whether or not it's true or false depends on what makes it up. As we're going to see, complex statements themselves are made up of simple statements plus one or more operators. So really, operators are the glue that connect all the little simple statements together. When you're thinking about actually using statement logic for constructing arguments or thinking about arguments, when we want to use it as a tool for actual argument analysis, when we're studying logic for the sake of its real-world application rather than as just an end in itself, as something to research and be interested in, what we need to do is see how the various sorts of statements fit together, because really when you're dealing with an argument, you're always going to be dealing with at least one complex statement. Because if you just have a series of simple statements and they don't actually connect to each other, then they're not really going to constitute an argument. So, and we've thought about this throughout the course. So look, if it's just a series of statements, they're not going to have the right kind of structure or relationship to each other. So if I say, well, my name's Carl, I'm wearing a blue shirt, the moon is roughly spherical, right? Those together don't constitute an argument. It's just a series of statements. It's a bunch of things that could be true or false, but it's not a series of statements. But if I say, if I'm wearing a blue shirt, then the moon is spherical, and I'm wearing a blue shirt, therefore the moon is spherical, all of a sudden, that's an argument. It's a weird argument. It's kind of stupid. I am wearing a blue shirt. The moon is spherical. But those two don't have a relationship to each other in the real world. The moon isn't spherical because I'm wearing a blue shirt. So there's an interesting question about what's going on there. But at least by putting it in those terms, I actually have an argument on my hands, not just a series of statements. So really what we're looking at in this chapter is precisely how logical operators that glue can hold together statements and put them in a form that turns potentially just a series of statements into an argument. So with that, let's go ahead and start taking a look at the third chapter here of the Formal Logic Primer. As I've done with the previous chapters, I've tried to make the little title text up at the top of the slides correspond to the relevant part of the actual text, so it's pretty easy to cross-reference, or at least that's my hope. So just before we get into actually looking at each of the operators, just a few more words on what they are and why we're looking at them. So operators connect what I call logical units. As we're going to see, a simple statement can be a logical unit on its own. Complex statements can also be logical units. So in their simplest form, and that's what we're going to look at in this chapter just as we're learning what operators are and how they function, operators connect simple statements together or operate on them, thus producing complex statements. So for our purposes here, within dealing with statement logic, a simple statement is just one of those statements that you can't reduce any further. It's the kind of thing that can be true or false on its own. We translate it and represent it by a single statement letter. Any single statement letter just on its own with no extra symbols or anything else is a simple statement. If you have more than just a single statement letter, you have an operator or it's connected to another statement by an operator somehow, then we're going to call it a complex statement. The truth of a complex statement is determined by the truth or falsity of its component statements. Now, as we're going to see in this chapter, we're only going to deal with component statements that themselves are simple statements. In the next chapter, in chapter 4, we're going to make things more complicated by seeing how we can actually connect complex statements with logical operators to make even more complex statements. So we boil everything down to simple statements, those tiny little pieces. We then take those little pieces and connect them together with operators. That works as the glue, and then we have larger statements. And then we can then combine larger statements together with more and more operators to make larger and larger things. So if you think about any sort of, well, I was going to say children's toy. It doesn't necessarily have to be for children, though. Anything, any kind of blocks or anything where you can put them together and construct things, such as Lego. No copyright infringement intended. I'm just mentioning it as a widely known version of this kind of thing. Or any other block-like thing like that, where you got all these tiny little pieces and they fit together in certain ways. They don't fit together just in any old way. There are only certain ways you can put them together. But you can take all those little pieces, put them together in the right ways, the ways that you can put them together, right? And you can keep doing that, and ultimately build up big and hugely complex things out of them. But ultimately, it's all just these tiny little component parts. In a sense, that's what we're doing with statement logic. We're using tiny little component parts, putting them together and building larger and larger and more complex things. As I mentioned already, all arguments within statement logic will require at least one complex statement to really have an argument on your hands. If you just have a series of simple statements, you don't have the right sorts of resources to actually be making inferences, actually making steps of reasoning, which are really characteristic of having an argument, right? That we've got sort of a statement that leads us to another statement. We've got a premise that leads us to a conclusion somehow. As we're going to see, the way that works in statement logic, the way that gets represented, is by having certain operators and then pulling together bits of information which allow you to then draw some sort of conclusion and make a step. All right. This last point, I think I've got ahead of myself, really what I was already saying. Not only can operators connect simple statements together to create complex statements, but complex statements themselves can then be connected by operators, making even larger logical units, even more complex statements. We'll see what that looks like when we look at chapter 4 next week. Okay, thinking back just a little bit, so in the first chapter we were talking about symbolizing an argument. What does that involve? Well, it involves taking all the natural language components and translating them into simple statements and assigning them a letter. There was one last thing that we couldn't do yet, which was actually show how those various simple statements relate to each other by using operators. When we put in the operators and we show the logical connections between the simple statements, we call that symbolization. So to symbolize an argument, first we have to translate it. We have to break it down to the simple statements, assign each of them a letter, and then we have to put in the logical operators, the glue, if you will, that shows how those simple statements relate to one another. So as I mentioned previously, I believe in my previous video, really what we're doing here is learning about a system. So statement logic has different parts to it and they all sort of fit together. And so what I've tried to do is pull that apart here and try to teach you pieces in order. You know, first thinking about translation, then thinking about truth tables, now looking at operators. All of these pieces sort of fit together, and by the time we hit chapter 5, hopefully you should see how it all fits together. Because in some sense, we're learning different pieces of one large complex thing. And so I've started where I think it's most reasonable to start. I'm trying to work through it in a way that makes sense and builds on itself. But as you're going to see, really, even when we're working in chapter 4, really by the end of chapter 4, you should see enough of these interlinking parts that when you're thinking about translating and symbolizing, you're going to have the tools at your disposal to be able to do that really well. One last thing, when we were looking last time at truth tables in chapter 2, we were really looking at this as our sample table, just P, Q, and then conclusion P and Q. Of course, P and Q can stand for any old thing. Now this is an argument statement logic. It might not look like it, because really what's going on is that we just have some statement P, say today is Friday. It really is, as I'm making this video at least. So look, today is Friday, P. Q, I'm wearing a blue shirt, which I am. Conclusion, today is Friday and I'm wearing a blue shirt. Now, normally speaking, we wouldn't really think about that as an argument because it doesn't seem like I've really done anything. I've just reasserted what I already said. We're going to see in statement logic that actually can constitute an argument, although a very boring one, because the conclusion P and Q is actually a complex statement that's held together. It's glued together by that operator and. We weren't able to fill in the column for the complex statements in the previous chapter. So in the previous chapter, really we were working through the steps we need in constructing a truth table, making the header row, so that row up top, and then also filling in the simple statement columns. Remember, we always have a number of rows after the header row equal 2 to the n. N is the number of simple statements in the argument. In this case, we have 2 statement letters, P and Q. So 2 to the power of 2 is 4. So we have 4 rows afterwards. And we need to make sure we represent every possible combination of the truth and falsity of the simple statements, in this case P and Q, which is what we have on this partially constructed table. We've got P, true, true, false, false. We've got Q, true, false, which gives us the 4 possible combinations of truth and falsity between P and Q. So now the outstanding question is, how do we fill in the row P and Q? How do we fill in that third column? How do we fill in the third column? Now, one thing to keep in mind, and we're only going to really come back to this in the next chapter, is that when we have a truth table, we need a different column for each simple statement. We also need a different column for each complex statement in the argument. We start with our simple statements on the left, and then we just add columns on the right for every complex statement we have on the argument. What we're going to see in this chapter are really the truth table definitions of the operators. This is why we started to learn how to construct truth tables and how to read them in the previous chapter, even though we couldn't quite finish what we started there, because now we're in a position in this chapter to actually learn the operators, fill in those complex statements, and it's going to work. It's recursive in some sense. We learn how to fill in the rest of the truth table based on the operators, and we understand what the operators are by filling in the truth table. Hopefully you're going to see what I mean in just a moment. So we have 5 logical operators that we're going to learn. Depending on how you learn statement logic, which can also be called propositional logic or sententional logic or sentence logic, you might have, typically you don't learn more than 5 operators. You might learn less. Quite often you can learn 4. you can actually do everything you have to do in statement logic with just two operators. There's actually even a way to just use one, but it's very unintuitive. So we're introducing and learning 5 operators in part because they help capture some very popular forms of thinking and reasoning. So here's just a small table of what those 5 operators are and the symbols we're going to use to represent them. And then for the rest of this video and in the rest of the chapter, really we're going to walk through what each operator means and how it functions and how it's defined in terms of the truth table. So the first one we're going to learn is negation, really just not, or saying something isn't true, it's false. The second one is conjunction. We've already been talking about that one. Conjunction really just tells us that 2 logical units are both true. So in a way, conjunction is almost unnecessary, but as we're going to see, it does play a very interesting and crucial role in being able to form complex statements that capture certain patterns of reasoning. Disjunction, or one thing or the other thing is true. Implication, if one thing is true, then some other thing must be true as well. And finally, the biconditional, if and only if, right? I'll come to the party if and only if, I don't know, my nemesis isn't there, or something like that. Of course, why did I go there for an example? I don't know. But anyways, let's move on. So these are our 5 operators we're going to learn: negation, conjunction, disjunction, implication, and biconditional. In terms of putting together simple statements and representing reasoning, we do all of it with these 5 basic operators and simple statements. We're going to see in chapter 4 that the use of brackets is also necessary to represent certain complex chains of reasoning, but all we're really doing with the brackets is adding an extra layer to our ability to stitch together simple statements with these operators. Okay, so let's take a look at each of them in turn. Negation is a unary operator. What does that mean? That means it's a one-place operator. It only affects one logical unit. It applies to the one thing that comes right after. The other 4 operators, conjunction, disjunction, implication, and the biconditional, are all binary operators. What does that mean? That means that they're a 2-place operator. So when we want to use them, we need to connect 2 things together, like a glue, this sort of glue that I'm talking about. So if my head is the operator, you need 2 things that it's putting together. If you have negation, you only need one thing. So the negation really just negates whatever comes right after it, as we're going to see. That's one key difference to keep in mind as we're looking through these 5 different operators. Negation really only applies to one thing. It only has one place to it. It affects one thing. The other 4 operators are 2-place operators. They have to connect 2 different things together somehow, but the way they connect them differs. Okay, so taking a look first at negation. A negation just tells us that the negated statement is false, or more broadly, tells us that the negated logical unit is false. Now, not is really the canonical English expression, right? When we say something is not the case, or it's not true that, or any similar kind of statement, we're really expressing a negation. And we're going to represent negation with the symbol, just really a minus sign or a dash. Often there are other symbols that are used as well. One thing I want to say up front, the symbols used in formal logic are arbitrary. Now, there are certain conventions and certain traditions, and different people like to use different symbols. And there is, in a way, some argument about which symbols are best to use, in part because they're the most popular to use. Now, we could represent anything with anything. That's an interesting part of representation. We could make negation a little cat face or something, right? We could make it some sort of complex drawing or something like that and represent the same thing. This could be a plus sign. There are, as I mentioned, other symbols that often get used. In some sense, it doesn't really matter. Now, I'm going to introduce a set of symbols to represent the operators within this version of the system that we're using. But if you learn statement logic or propositional logic or sentence logic from someone else or somewhere else, be warned that it's highly likely that you might have to learn some new symbols. It just comes with the territory. But keep in mind that the actual operators themselves don't change. Though, one other thing I'll mention, I'll just say it here, don't worry about it too much. You can produce other operators. So if you look online and just sort of look up propositional logic or statement logic and look up operators, there's actually a whole bunch of different operators you can use. But like I said, the ones that we are going to use here are the ones that most closely represent our normal patterns of reasoning and thinking. Now, we can understand how negation works with a truth table. So this is really the truth table that just defines negation. So the truth tables we're going to look at in this chapter are definitional. They just define how the operators work. So in this case, what do we have? Well, really, we actually only have 2 rows. Now that might seem weird because you look at it and you say, well, we've got 2 different columns. We do, but we only have one simple statement, P. We always have a number of rows in addition to the header row equal to 2 to the power of n. If we only have one simple statement, that means we have 2 to the power of 1, which is just 2. So we only have 2 rows. And if you think about it, if you just think about P, any statement, it's either true or false. That's it. If you take a look at the table here, on the left column, we've got P, and on row 1, P is true, and on row 2, P is false. Now, if we take a look at the second column, that's the one that represents not P, or the negation of P. As you'll see there, not P is true when P is false, and not P is false when P is true. Not P just has the opposite truth conditions of P. That's really all it is. So if P is true, not P is false. If P is false, not P is true. Or if you switch it around, when not P is false, P is true. Or when not P is true, then P is false. So not P, or the negation of P, is really a complex statement because we have a simple statement, P, and then we have an operator, not. Pulling those together, not affects one thing, one logical unit. In this case, it's just a statement, P. Not P is just asserting that P is false, or it's not the case that P is true, or you could put this in any other way you'd like as well. Now, there are a couple of fairly simple rules to keep in mind when you're dealing with negation, when you're trying to construct negations, when you are doing some translating work. One is that a double negation is equivalent to an affirmation. So not P is really just the opposite of P. Right? If P is true, not P is false, or if P is false, not P is true. That might still seem weird because not P is really just saying that P is false. So if not P is true, we're really saying it's true that P is false, right? Well, what does that mean? It really just means that P is false, which you can think about it differently. Saying P is false is just the same as saying, well, it's not the case that P, right? So look, let's just take for P, today is Friday, right? Or given that I'm making this video on Friday, let's take today is Wednesday, right? If P is today is Wednesday, not P is just saying it's not Wednesday, or it's false that today is Wednesday, or it is not the case that today is Wednesday. Now, given that this is actually Friday I'm making the video, when I say it's not the case that it's Wednesday, or it's false that today is Wednesday, the statement that it's false that today is Wednesday is true right now on Friday, right? Similarly, if P is Carl is wearing a blue shirt right now, right? Not P is just saying it's false that Carl is wearing a blue shirt right now. So maybe I should switch it. I say I'm wearing a green shirt right now. Say that's P. Carl is wearing a green shirt right now. Well, it's actually false that I'm wearing a green shirt right now. So P would be false. So not P would be true. It's actually true that Carl is not wearing a green shirt right now. Or it's not true that Carl is wearing a green shirt right now. Or it's false that Carl is wearing a green shirt right now. All of those 3 statements just add up to the same thing. It's really just a negation of P. So saying P isn't true, whatever P is. Now, if we take a look at number 1 up in the box on the right there, first rule, a double negation is equivalent to an affirmation. So we can actually string together negations. We're going to learn more about this in the next chapter. But you can have P, you can have not P, you can have not P. A double negation, not P, is the same as really asserting P. Now, we typically avoid double negations in written and spoken language, or at least we try to. So we tend not to say, it's false that today isn't Wednesday, right? Or really, given that it's Friday, it's false that today is not Friday. What does that amount to? The claim that it is Friday. Because of course, if it is Friday, and I say it's not Friday, then that's false, right? I'm saying it's just isn't Friday. It's false that it's Friday. If I say it's not the case that today is not Friday, I'm really saying it's false that it's Friday, right? And if it's false that it's false, then it's true. That might seem weird, and I'm not trying to get you extra confused, but it's just the way it works. You can even string together more negations. You could have a triple negation or a quadruple negation. You could say if not the case that today is Friday. Now, I'm not going to pose anything like that to you, but just keep in mind that if you do wind up with a double negation somehow, it's the same thing as an affirmation. Not is equivalent to it just is. Second, this is a more important one to keep in mind. As a rule, when you're translating from natural language, such as English, into simple statements, putting your information into the form it needs to be able to work with it in statement logic, as a rule, translate statements as affirmations, then negate them as necessary. So if you encounter something in natural language, say English, right? Somebody says something like, today is not Friday. Translate that statement as today is Friday. So say P equals today is Friday, and then negate the statement. So then say not P. Why do it that way? Why not just translate the statement as P equals today is not Friday? Why? Because if you then go on to negate that statement, which itself already has a negation in it, then you're going to have to invoke the first rule much more frequently. So if your statement already has a negation in it, and then you negate the statement, ultimately you're affirming something. So if you take the statement, today is not Friday, you then make P, today is not Friday. Not P is saying, it's not the case that today is not Friday, which really amounts to the claim that today is Friday. And that's just confusing. So as a rule, translate statements as affirmations. Talk about what is the case, what is true, what is happening or has happened. Then negate the statement after you've translated it. If you stick with that rule or really that convention, it should make your translating and then thinking about what you're actually doing with your translations just that much easier. Okay, let's take a look at a couple of examples. Now, unfortunately, I've already worked through this first one because it's what I always reach for. You know, P, today is Friday, right? Not P is really just saying it is false that today is Friday or today is not Friday, right? Now, we've got two different sentences there in English, but they really amount to the same meaning. They don't really have any extra meaning that isn't captured by just negating today is Friday. Another one, Carl is working from home. I am right now. So if Q is Carl is working from home, not Q will be just something like it is false that Carl is working from home, or Carl is not working from home, or it is not the case that Carl is working from home, right? Or anything like that, anything that has that meaning, we can really represent in this fashion. Okay, let's take a look at our second operator, conjunction. A conjunction simply asserts that both conjuncts are true. Now, we normally find conjunctions in English with the word and, not always. So be careful. When I'm giving you these canonical English expressions, these are the English expressions most often associated with these relationships between statements in English, but it's not always the case that if you see the canonical English expression, you definitely have the operator functioning, and you can have times where the operator is functioning where you don't see that canonical English expression. So you have to think in terms of, when you're doing translating, you have to think in terms of what are the relationships between the truth values in these statements. What is somebody really trying to say when it comes to whether or not statements are true or false? And of course, being able to do that is something you can only really successfully do once you have a sense of what these logical operators are, which is why we're learning them here. Now we represent conjunction, or and, with this symbol, the ampersand. There are other symbols that can be used to represent it, including quite often a dot, or sort of it's almost like a triangle that's missing the bottom. We're just going to use the ampersand because I think for virtually all of you, that already means and to you. So I think it's pretty intuitive to use it here. Now, that argument we were looking at in chapter 2, PQ, P and Q, we looked at the completed truth table of it earlier, and then we worked on getting ourselves back up to that. How do we actually construct that truth table? Well, it turns out that that argument, that truth table that we looked at after it was completed, was actually just the definitional truth table for a conjunction. So if you look up at the top again, where I say a conjunction simply asserts that both conjuncts are true. So if we look at the truth table now, we've got P and Q as separate columns, right? We've got a column for P and a column for Q. We now have 4 rows because we have to represent the 4 possible combinations of true and false between P and Q. And we're going to see for the rest of the operators, we have a truth table like this where we have a row for P and a row for Q, and then a column for P and a column for Q. My apologies. And then a column for the actual complex statement that involves the operator. Now, one thing to keep in mind, we're using P and Q here just for explanatory purposes. On these definitional tables, P and Q stand for anything, any logical unit. So it could be any simple statement. You know, P and Q could be R and S, or A and B, or, you know, whatever you want, K and T. It doesn't matter, any simple statement. Those could also be complex statements themselves. We'll learn more about that in the next chapter. But if we just return our attention to this table here, and we keep in mind a conjunction simply asserts that both conjuncts are true, when we look at the table, we then have to ask ourselves, how do we fill in the truth values for the complex statement P and Q? Well, we look to the only row where P and Q are both true. That's the first row. So that's the only row where P and Q, as a complex statement, is true. And the other 3 rows, at least one of them is false. Given that a conjunction is asserting that both conjuncts are true, it's only in the first row that that's actually the case. So it's only in the first row that that complex statement is true. Now, I've been using this word conjunct. When we're dealing with a conjunction, it always connects 2 logical units. Right, so either 2 simple statements or 2 complex statements, or it can even combine 1 simple statement and a complex statement. Again, we'll look at this more thoroughly in chapter 4. So keep in mind, a conjunction always connects 2 logical units. In this case, our example, 2 simple statements. And each logical unit in a conjunction is called a conjunct. So I've been saying, and right at the top where I say a conjunction simply asserts that both conjuncts are true, what do I mean? You've got the conjunction in the middle, right? Again, let's just say it's my head. You then have 2 logical units. The conjunction connects those, it glues them together. Each of those logical units, because they're being connected by a conjunction in the middle, we call them conjuncts. Each of them is called a conjunct. So whenever a logical unit is connected to another logical unit by a conjunction, we refer to the logical unit as a conjunct. Now, it's as I've already been saying, it's really this last column, the P and Q column, where the truth values of P and Q together, that complex statement, are determined by the truth values of the simple statements. So we have to read across and we look. Conjunction's only true when both conjuncts are true. Now, for the sake of explanatory purposes, I'm going to put together, just in a Word document, some truth tables. And they're going to really just be really what's going on here. I'm just making these truth tables again, but just to show you what that looks like, because when you're doing your own work, when you're translating statements, right, and you're symbolizing them, when you're writing the final exam, you're going to have to do that in an electronic environment. So you're going to have to be able to make tables and then fill them in the right way. so I'm just using Microsoft Word here. Now, if I go up to the Insert tab up here on the ribbon, you might have your ribbon collapsed, but if you click Insert, then under there, there's the Table option, Add a Table. So we click that. And when you click that, it then pulls up, and you can choose how many rows and how many columns your table is going to have, right? So you can, if you know ahead of time how many you need, you can just put that in. You can add them later as well. So look, I can make a 2x3 table, and then I'm going to go ahead and, even though I'm on here, I'm going to select that. I'm going to center, because that's just how I want to see it. I'm going to put on caps lock. Let's just do the first table again. So we've got P and we've got not P. And just fill that in on the table. All right. I'll go ahead, I'll make those bold just to show that's our header row. Now under P, I just need to fill in the truth values for the simple statement P. P is either true or it's false. That's it. Right? Now, and if you think back to how do you fill in the values for simple statements, either method of doing that would have gotten us the same result here. So we just have true and false. Now we go over and think about not P. How do we know what value to fill in? Well, we have to go back and look at the value in the simple statement column. So when P is true, not P is really just the opposite of P. It's just saying P is false. So in this first row, if P is true, then not P is going to be false. In the second row, where P is false, not P is going to be true. That's it. And so no matter what we have, in terms of initial statement, what we're trying to negate, we're always going to wind up making the same table. Let's just say we had Q. Right? Q, and so we wanted to have not Q instead. Make that bold. It's just the same thing. Q is either true or false. Not Q is false whenever Q is true, and not Q is true whenever Q is false. That's it. Now, let's just move on to conjunction. Now, when we were looking at conjunction, let's go ahead and we'll just pull this back up for a second. In looking at conjunction, we have to make a different table. In this case, for this specific table where we're just showing what conjunction is, we've got 3 columns, and in total we've got 5 rows. We've got the header row and then 4 rows after it. So let's go ahead and put those in here now. So we have to do a table. You know, we're gonna have 3 columns and then 1, 2, 3, 4, 5 different rows. And then what are we gonna do? Well, same thing. And again, I'm going to center it. Right. Put on bold for a second. I've got P, I've got Q, I've got P and Q. P and Q. All right. We'll make that all bold. Now, how do I fill in the simple statements? Well, we can use either of the 2 methods. I'll start with the first method here. We fill in half and half. So I've got 4 rows, so that's true, true, false, false. Now for Q, we've moved over a column. So at this point, we need to have the number of trues and falses we put in at a time. Given that it's our last simple statement, we know we're just going to wind up alternating true, false, true, false. So we'll just do that, true, false, true, false. Right? We put in 2 trues at a time in this column, so we only put in 1 at a time in this column. We went true, true, false, false in the first one. So over here we go true, false, true, false. Then we have to think about the conjunction P and Q. Now we're trying to figure out how to fill in the values of a complex statement like P and Q. We don't have a method of filling them in like we do for simple statements. You don't have to go true, true, false, false. Instead, whether or not a complex statement is true depends on the truth values of the logical units that make it up. In this case, our logical units are P and Q separately. Those 2 simple statements. Our one conjunct is P, the other conjunct is Q. The conjunction is only true when both conjuncts are true. So if we look at a truth table, in the first row, are both conjuncts true? That would mean P is true and Q is true. That's what we see. They're both true. So we fill in the value, true. We then just go to the next row. P and Q, the complex statement, is only true if P is true on its own and Q is true on its own. What do we see? P is true on its own, but Q is false. Q is actually false in that second row. Only P is true. But P and Q, the complex statement, is only true when both are true. So we only have one being true, which means P and Q, the complex statement, is false. Move to the next row. That complex statement's only true when both are true. What do we see? P is false, but Q is true. Both have to be true for the complex statement to be true, but only one is true, so the complex statement is false. In the last row, same thing. The complex statement P and Q is only true when P is true and Q is true. And in the last row, P is false and Q is false. What does that mean? That means our complex statement is false. And that's just an end to it. There just isn't any more to it than that. So, with that, we'll go back to taking a look at our other slides here. One thing I just want to iterate here before going on and showing more operators is that it can be kind of tricky to learn these operators. So you might want to go through this material more than once and even just watch this video more than once if you can stand it. If not, just stick with the material. But really, the important thing that we're learning in this chapter is just how to fill in the truth values of complex statements. The truth tables we're looking at really just define them for us. So when we look at that example, the conjunction truth table we're looking at, and I'm saying, well, look, the conjunction asserts that both conjuncts are true, so it's only in that first row where they're both true that the conjunction P and Q is true. Or you might say, but why is that? Why is it that the conjunction is only true in that first row? It's true by definition. That's just what the conjunction is. That's just what it means. When we are asserting a conjunction, that's what we do in natural language. And when we're using statement logic and we're using this artificial language, when we put in that ampersand, that and sign, when we're representing the conjunction operator, we're just saying that both conjuncts are true. That's just what it is. Okay, so with that, let's go ahead and pick back up with where we were in our slideshow. So we're at slide 7 here, looking at conjunction. So let's look at an example. This is an example right out of the book. Carl and Yoda went for a walk and smelled beautiful flowers. Right? My dog Yoda and I. Now, if we want to translate this, we're going to have Carl and Yoda went for a walk, and Carl and Yoda smelled beautiful flowers. So in the example, we actually have the conjunctions show up between Carl and Yoda, and between walk and smelled beautiful flowers. Right? Went for a walk and smelled beautiful flowers. Now, you might look at the translation and say, that seems a little funny. Why would we say Carl and Yoda went for a walk is P and Carl and Yoda smelled beautiful flowers for Q? Couldn't we break that apart? Couldn't we say Carl went for a walk? Separately, Yoda went for a walk. Separately, Carl smelled beautiful flowers. Separately, Yoda smelled beautiful flowers. Yeah, in a way we could do that. Now, look, in the way I have translated it here, P and Q, when we assert P and Q, the complex statement, we're just saying that both P and Q are true, right? So really, what are we doing here? In some sense, we have the natural language statement at the top. We're breaking it down into simple statements. We're translating them. And then we do the conjunction. We're just showing that the simple statements are both true. They fit together. In some sense, we're working our way back out to the original complex statement, right? If we assert P is true and Q is true, what are we saying? We're saying Carl and Yoda went for a walk and Carl and Yoda smelled beautiful flowers. Now that's a little bit more wordy than the original formulation, but it's also very clear. Now, this issue that I was talking about and sort of broke off and was just sort of talking about what we're doing in terms of going from the natural language into the little pieces and then back to the natural language. This issue about where and shows up, and this relates back to what I was saying, that it's not always the case when you see and in natural language that you have a conjunction that you have to break apart in the translation. Why is that? Why? Because sometimes when we're looking at what's being said in natural language, what's really being said is that two or more people or creatures or things have some kind of property. Something's being said about them. Now, I said we could take what we have here, we could break it down and say Carl went for a walk, Yoda went for a walk, Carl smelled beautiful flowers, Yoda smelled beautiful flowers. We could break that first sentence down into those 4 different simple statements. Why shouldn't we? Well, we shouldn't, precisely because we can't then conjoin them, string them together with a series of ands, and really recapture the meaning of the original statement. When we take a look at the original statement, Carl and Yoda went for a walk and smelled beautiful flowers. What's really being said there? Almost certainly, and I could have altered the example to make this explicit, that Carl and Yoda went for a walk together, and that Carl and Yoda smelled beautiful flowers together. We could have put that into the original natural language statement. In fact, if somebody said this, if I said, somebody said, Carl and Yoda went for a walk and smelled beautiful flowers, you might look at them and say, together or separately? Presumably, if they're saying this, they mean together. They might mean separately. But if they do mean together, and if they had said together, then we should really translate it into Carl and Yoda went for a walk together, Carl and Yoda smelled beautiful flowers together. So we could add even more information to try to make it more specific. But if we break it down into 4 simple statements, we say Carl went for a walk and Yoda went for a walk. Right? Let's just take those 2 for now. And you asserted both. You assert P and Q. P, Carl went for a walk. Q, Yoda went for a walk. What would you be saying? Well, you'd be saying Carl went for a walk. That's true. Yoda went for a walk. That's true. Now there's a question. Did they go for a walk together, or is it just separately true that each of them went for a walk on their own? Right? It seems like we're really saying the latter, or at least that seems to be what's represented. So what we lose by breaking down certain instances of and in English into like completely just getting rid of them is that we start to lose some of the original meaning. When people say things like Carl and Yoda went for a walk, and they mean that they did it together, we need to try to preserve that meaning in our translation. That can be something a little bit tricky. When should you view an and as actually signaling a conjunction you should get rid of, and when shouldn't you? I put it back and really say, think about what the original meaning is. Are you going to be losing the original meaning by separating them out? We can't really represent together by using our logical operators. We can, however, stitch back together the current translation of P and Q to get what's effectively the original meaning based on the truth conditions. What makes the first natural language sentence true or false is really the same state of affairs that makes P true or false and Q true or false. It makes the 2 of them together true or false. We just don't have any operator that would represent something like together. So we need to be sensitive to that fact when we're doing our translations. This is another reason why really what we have here is a system of interlocking parts. We're working our way through each of those parts, learning how each of them works, but then it's only really seeing them all in action together do you really understand how the whole system functions. It's just like learning about a machine. If you learn about a certain kind of engine, the engine's made up of all sorts of different parts. All those parts interact with each other. But you can learn about the parts separately. You still have to learn about how they interact with each other to have a full understanding of how the machine actually works, how it runs, how it functions. What we're learning is something that functions. So we have to learn all the pieces and then see how they all work together. That's what we're working towards. Okay, now with that, let's just go back to our Word document. Oh, no, I'm sorry, I'm getting myself tripped up here. Okay, so that really finishes our look at conjunction. Let's now look at disjunction, our next operator, our third operator. This is typically represented in English with either or. Often it's just or. Statement logic uses the inclusive disjunction, not the exclusive disjunction. What's the difference between them? The use of or in English is often exclusive. When we say something like either Jill did it or Steve did it, that typically means that either Jill did it or Steve did it, but not both Jill and Steve did it together. Right? That's the exclusion. We're excluding the possibility that both things are true or that both things happened. When we use disjunction inclusively, we're allowing for the possibility that both of the things are true. Right? So we say either Jill did it or Steve did it. This really means when we're using or inclusively, that either Jill did it or Steve did it, or both Jill and Steve did it potentially together. Right? Now that might sort of creep in the together bit from what we were just talking about from the previous one. As you're going to see, that's not always the case, really all the inclusive disjunction is allowing for is the possibility that both things are true, even if the two things are completely unrelated to each other. Now this understanding of disjunction first can always be used for good jokes. If somebody is giving you a choice between two things and you like both of them, you can just say, yes, please, both. Right? They might give you an odd look, and then you can just tell them to go study formal logic. One of the fringe benefits of knowing about formal logic is being able to crack formal logic jokes and have about 3 people understand what you mean. So let's take a look at the truth table for the inclusive disjunction. What we're looking for on that table, and really the definition of the inclusive disjunction, is this. An inclusive disjunction claims that at least one of the disjuncts is true. At least one of the disjuncts is true. So a disjunction is true when at least one of the disjuncts is true. We're going to represent the disjunction with a V symbol. In terms of typing it, feel free just to use a capital V on your keyboard, and then just be careful not to represent anything else by V. Though we're going to see, as we learn more rules about how to use these operators in the next chapter, even if you used a V to represent a simple statement, there shouldn't ever actually be a case where a reader of what you're writing down should get confused, as long as you're formulating everything properly. But just as an easy tip, don't use V when you're making translations, just because it looks an awful lot like one of our operators. So, well, I'm going to go ahead and stop for a second, because I just found a typo in the slides. And so I better correct that now before I just leave it up there and make it very confusing. Okay, let's go back to what we're looking at. So, the disjunction claims at least one of the disjuncts is true. What does that look like on our truth table? Well, the disjunction truth table looks like this. As you'll see, the rows for, or the columns for our two simple statements, P and Q, are still there, and they look exactly the same. That's one thing you can rely on. If you have a truth table that has two simple statements, the simple statement columns will have, up in the header row, you'll have each of the simple statements, and then you're just going to see this below it. It'll be true, true, false, false, true, false, true, false. That's just how it works. It has to work like that. We're going to see as we move on and start looking at more complex tables, if you have 8 or 16 rows, you're going to have exactly the same kind of pattern, that you're going to have a column for each simple statement, and then all the rows below the simple statements are going to look the same. The only thing that's going to differ on longer and more complex tables are the truth values for the complex statements. This is part of why we're learning how the operators work, because by knowing how the operators work, you can then fill in what those values are and then actually figure out whether or not an argument is valid. So looking at our table, so we've got P, true, true, false, false, Q, true, false, true, false. If we then look over at P or Q, that's what the symbols are representing here. We've got P, we've got the V in the middle, that's our sign for or, then we've got Q. Well, as we know, the disjunction claims that at least one of the disjuncts is true. So if we take a look at it, we've got for rows 1, 2, and 3, the disjunction is true. It's only in the last row that the disjunction is false. Now, the disjuncts that the disjunction connects are really the two logical units. Just like with the conjunction, whatever the conjunction connects, you call conjuncts. The disjunction, whatever they connect, you call disjuncts. Right? So whatever those two things are. In this case, it's P is one disjunct, Q is the other. It could be anything. It could be two different letters, could be R and could be K, or it could be even more complex things. So in that last column, the P or Q column, we see that it's only in the last row, the fourth row, where both disjuncts are false. P is false and Q is false. It's only in that situation that the disjunction is false. As long as one, the other, or both disjuncts is true, then the disjunction is true as well. So if we just go back for a second to our Word document, we can go ahead and make this table that we're looking at there. We're going to have the same thing. We've got 3 columns. We have 5 rows, the header row. So we have P, Q, P or Q. Go ahead and center that and bold that. And under P, we've got exactly the same thing as we're usually expecting. We've got true, true, false, false. And then under Q, true, false, true, false. And then over at P or Q, we've got true, 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 false. And how do we figure that out? Just by reading across. So if I go ahead and delete these here, if we're looking at row 1, the disjunct is true as long as at least one of the disjunction is true as long as at least one of the disjuncts is true. Both disjuncts is true here, so it's true. Second row, we read across again. P or Q is true as long as either P or Q or both of them is true. P is true, so P or Q is true. Same thing in row 3, right? Is either disjunct true? P is false, Q is true. So it's true. In the last row, they're both false. So we take a look and we say, okay, the disjunction's true as long as at least one is true. Is at least one true? No. So the disjunction is false. Let's take a look at an example here. This is a good example. I like this one. You can have cookies or cake for dessert, right? So P, you can have cookies for dessert. Q, you can have cake for dessert. P or Q really translates into, and you can see how this is wordier than the original, which is part of why we usually don't talk this way. You can have cookies for dessert, you can have cake for dessert, or you can have both cookies and cake for dessert. Right? You have one or the other, or both if you want. This is why I say there's some pretty good jokes that you can make if you learn this material. Somebody says you can have cookies or cake for dessert, and you go, yes, please. You probably say, well, which is it? You say both. You told me I could have both of them together, didn't you? And then presumably if they say no, you can accuse them of not being clear about what they meant in the first place. Right? Probably get thrown out of the establishment if it's somewhere that you're buying something, or just not get invited back. It's a friend's place. So this is really just how disjunction works. We've got disjuncts, separate simple statements or other complex statements. The disjunction is just saying at least one of them is true. At least one. Okay, on to section 3.4, the implication or conditional statement. Now these sorts of statements typically capture causal or logical relations. They can also represent rules. So for instance, if the cause occurs, then the effect occurs. Right? There's an if-then statement. Implication or conditional statements are really of this kind. Rules, if you punch the goalie, then you'll be removed from the game, or you'll get a penalty or something like that. I used that example in the book a fair bit. Logical relations. If P is true, then P or Q must be true. We'll see what that looks like as we go on. Note here, I'm using lowercase letters in the example. As I said earlier when we were looking in chapter 1, it doesn't matter if you use upper or lowercase letters. You can use either. Just try to be consistent once you started using them in one place rather than another. I know you can now accuse me of being inconsistent, but at least this is a different slide. So I'm just trying to, in some ways, mix things up a little bit just so you can see some of the differences. And at least here and there, I'll use things other than P and Q. I'm trying to stick with them largely for now, just in defining everything. But as we move forward, I'll try to mix it up at least here or there, just to remind you that it doesn't have to be P and Q. We're just using those for explanatory purposes. So implication statements have this kind of form. As you can see, the sort of if-then. You only see if-then in English. Sometimes it'll just be if something, 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 right? If the cause occurs, comma, the effect occurs. In that case, you've really got sort of a missing then. Sometimes if-then statements are missing from an argument entirely. Somebody will say something and then draw some kind of conclusion from it because it's thought to just be obvious that something will happen, right? Saying I'm trying to do something electrical, right? Well, if the electricity's on, I might get injured if I then go ahead and start touching electrical wires. So somebody looks at me and says, the electricity's on. You shouldn't touch that unless you want to get hurt. What are they really saying? If the electricity's on, then when you touch that, you're going to get hurt, right? Assuming you don't want to get hurt when you touch it, so you should probably go turn the electricity off. It's capturing a certain kind of implication statement. So an implication statement, so the complex statement that uses the implication operator is claiming that if the antecedent is true, then the consequent must be true as well. Really, what it's telling us is that it's impossible for the first thing to be true and the second thing to be false. The first thing is the if thing, the second thing is the then thing. As you can see, the definition of an implication statement itself includes an implication statement. Look at the definition. An implication claims that if the antecedent is true, then the consequent must be true as well. Right? That's really how it works. That's what it's saying. In some ways, this is a basic feature of our thinking, that we can think this way. We can go, this thing gets that thing. If this thing is true, this thing's true. If this thing happens, that thing's going to happen. Right? We somehow relate events together in our minds or in our brains. We'll sort of leave that open about whether or not minds are just brains, or if there's something else going on there. Also, what the actual mechanism is, I don't know. But that's a great thing to talk to psychologists and neuroscientists about. So, this canonical English expression looks something like this: if, then, right? And those ellipses, those dot, dot, dots, that just means you're going to have anything at all in there. So if we look just back to the definition, an implication claims that if the antecedent is true, the antecedent being true is what's going in the dots, then the consequent must be true as well. Come after the second set of ellipses. We symbolically represent this operator with an arrow. Now this is just the arrow that Microsoft Word and PowerPoint just sort of produces. If you put together two minus signs or short hyphens and follow it with the little, oh goodness, I forget the name of the thing. It's kind of like a sideways triangle beside the question mark. I really should have looked that up because now I seem pretty goofy, especially for those of you that know what that's called. It looks sort of like a little right arrow. So if you go dash, dash, little right arrow, it'll produce exactly what I'm using here. Now, typically in logic, the arrow itself is sort of a little bit longer. It's got a longer stroke to it. But for the sake of just simplicity, I've just been using this one. And if you can't construct that one, if you just go dash, dash, and then that like right triangle, sort of down by the question mark, as long as it's clear you've got something that looks an awful lot like an arrow, that'll be fine for our purposes. So we just write it out like that, P then Q. Now, this is probably the trickiest operator to understand for a lot of reasons. So I just want to, in some sense, restate that initial point. So that initial point at the top, an implication claims that if the antecedent is true, then the consequent must be true as well. We can state that a little bit differently. An implication statement is false when and only when the antecedent is true and the consequent is false. The implication statement is really committed to a fairly minimal statement that the truth of one thing implies the truth of another thing. Right? That on condition that the first thing is true, then the second thing will be true as well, definitely. Now, given that that's what the statement's saying, that statement's only false when the first thing is true and the second thing isn't. Because all the statement said is that if the first thing is true, then the second thing will be true as well. Note, it's not saying that the first thing really is true, right? It's just saying that if the antecedent, if the first thing is true, then the second thing will be true as well, right? If can be hypothetical, right? It depends. Might be true, might not be true. So like disjunction and conjunction, the implication operator always connects two logical units, right? So it takes up a middle position. There's always something on either side of that. And those can be simple statements or complex statements. The first logical unit, the one after the if, is the antecedent. The second logical unit, the consequent, is what we call the consequent, right? After the then. So in disjunction and conjunction, we call both logical units that are being glued together by the operator, we call them either conjuncts or disjuncts. And the implication statement, there is a difference between them, and it's a very important difference. We call the thing after the if, the first thing, the antecedent. We call the thing after the then, the consequent, right? So you can think of antecedent really, it means, the actual word, something like what comes before, right? The consequent is the consequence of that thing, the result, what happens. So keep that in mind. One other thing to keep in mind is that when you're translating from natural language into the pieces you need to use statement logic, translating it into simple statements and symbolizing, it is just not always the case that in natural language, the antecedent is said first and the consequent is said second. Sometimes we flip those things around. So you might say, what? If it's cloudy, then it will rain. I'm already jumping ahead and sort of using an example I'm going to get to, but we'll see a little riff on that. If it's cloudy, then it will rain, right? So the antecedent would be it is cloudy, consequent, it will rain. But you might have somebody say something like, it will rain because it's cloudy. Right? Now, that could just be an explanation, but it's also an implication statement in some sense. And so depending on the context it's uttered in, if it's actually part of an argument, that's probably equivalent to the implication statement, if it's cloudy, then it's going to rain. Right? Other words can sometimes be used as well. So really what you have to ask yourself is, if it's an argument, and it's the context of the argument, are they really trying to connect things in this sort of way, saying that the truth of one thing really depends on the truth of another thing? If so, you're probably dealing with an implication statement. So let's take a look at the truth table for this. So as we already noted, the first logical unit, right, the one on the left of the arrow, right, the one the arrow is pointing away from, is the antecedent, what comes before. The thing that comes after the arrow is the consequent, the result. Now, when we look in the row for the truth values of the complex statement itself, so the implication statement, we see it's only false when the antecedent is true but the consequent is false. So it's true in the first row because both the antecedent and consequent are true. It's true in the third and fourth rows because the antecedent is false. And it's only false, the implication statement is only false in the second row because the antecedent is true while the consequent is false. All the implication statement is committed to is saying that if the antecedent is true, then the consequent is true as well. That's what we get up in row 1, right? If P is true, then Q is true. That's really what the implication statement is saying. So that condition is true. In the second row, the implication statement's false because it's saying if P is true, then Q is true. But in the second row, we see P is true and Q is not true. So if that's the actual situation we find ourselves in, then the implication statement is false. In the third and fourth rows, P is false, but the implication statement is true. Why? Because the implication statement is really only committed to saying row 2 can't happen. It can't be the case you have the antecedent without the consequent. What about cases where you don't have the antecedent? P is false. The implication statement just doesn't really say anything about that. It's not trying to make an assertion about what happens when P is false. So the statement can still be true so long as it's never the case that P is true while Q is false. So something to keep in mind. Now we've got an example here and then a few more clarifications because this is a tricky operator. So look, another example. If I press the space bar, the presentation will advance to the next slide. Like, that's true about what I'm doing right now. I've got this presentation. If I hit space, I get the next slide. Well, I guess the next thing comes up, and if I'm at the end of it, then I get to the next slide. So look, P, I press space bar. Q, the presentation will advance to the next slide. We represent this as if P, then Q. That's just how we'd say this, right? We could also say, P implies Q. That's another way to say it. And really what we're representing is just that initial statement at the top. If P is true, if I press the space bar, then Q is true. That is, then the presentation will advance to the next slide. And see, even in this example, then isn't actually said there, but it's implied. You can see it, right? So if P, then Q is only false if the presentation doesn't advance to the next slide when I press spacebar. It remains true even when I don't press it. So this statement, if P then Q, it's just saying if I press the spacebar, here's what's going to happen. We're going to go to the next slide. We're at the end of the slide, so it's actually going to happen this time. That is only false. The complex statement, if P then Q, with this content, right? This meaning for P and this meaning for Q. That statement, if P then Q, is only false if I press the spacebar and we don't go to the next slide. Right now, I'm not pressing the spacebar, right? Hands off. I'm not pressing it. So the statement, if P then Q, is true, even though I press spacebar, is right now false. let's see what happens. I'm going to press the space bar. What's going to occur? Look at that. We went to the next slide. So that statement was true, right? If I press the space bar, then I'm going to go to the next slide. Even when I wasn't pressing the space bar, it was still true that whenever I did press it, something was going to happen. So the only time that kind of statement is false is if the antecedent is true, but the consequent is false. So let's think about, I had that example. If it's cloudy, then it's going to rain. That statement, that complex statement, if it is cloudy, then it's going to rain, altogether, is false if it's ever cloudy, but it doesn't rain, which happens. Sometimes it's cloudy, right? So the statement, if it's cloudy, then it will rain, or then it is going to rain, that's actually false. It's just not a true statement in our world, right? Look, I've got a pencil, right? If I drop the pencil, then it will fall, and it does, right? If I drop the pencil, then it will levitate in the air unsupported by anything. False, right? I made an if-then statement. The antecedent occurred. I dropped the pen. I let go of the pen. It didn't hover. It didn't levitate. So that statement, if I drop the pen, then it's going to fall, is false. Okay, a few more things to keep in mind with implication statements. Like I said, this is the trickiest one. I recommend certainly reading this section of the text. I go through some of these issues in a little bit more detail there. You should get all the important points here, but especially if you have questions arising from any of this, go look at the text. Look at section 3.4 in particular. I've got quite a bit of discussion about this operator. So look, first, if the implication statement is true and the antecedent is true, the consequent must be true. I'm really just reiterating what I've already said there, but when we're thinking about probability, this becomes very important. The implication statement is a 100% relation. If it's saying that if the antecedent is true, then it must be true, 100%, that the consequent is true as well. That is just what it means. So there's no probability in statement logic in the inductive sense that you might have a true premise, and if you have an inductive argument, it gives you reason to believe the conclusion, but it doesn't guarantee that the conclusion's true. Deductive arguments get the guarantee. That's what makes them deductive arguments. An implication statement doesn't say if this is true, then, well, that might be true. It's saying if this is true, that has to be true. The consequent will be true 100%. Now, of course, we should have some room for probability somewhere, right? If statement logic can't somehow represent probability, then it seems like it really is a big shortcoming. We can put probability into statement logic by placing it within a statement. So look, we're thinking about if it's cloudy, then it's going to rain. So look, here I've got C and R, just to mix it up. Statement C, it is cloudy. Statement R, it will probably rain today. We go ahead and we symbolize that. We're going to have, right, if it is cloudy today, then it will probably rain today. The probably is now part of the statement R, right? But the relationship, the implication relationship between C and R is a 100% relationship. If C is true, then R has to be true as well. It just turns out that R's being true, full stop, flat out, now itself means that something else is probably going to happen or probably be true. So we can put probability into statement logic this way. That's a pretty handy thing to keep in mind. So if you're looking at an argument, you say, I believe this is deductive actually, because I can represent it this way, but I have this probabilistic element, what do? Put the probability right into the statements themselves. Arguably, all inductive arguments can be translated into deductive arguments by following this kind of translation procedure. I say arguably because I can think of at least one person, a colleague of mine, who would likely argue with me all day about why that's false, why I shouldn't have even said that or suggested it. Now, I'm not going to fully commit myself to actually saying you can adequately represent all inductive arguments in a deductive system like statement logic, but there's certainly some flexibility there. So when you're looking around for arguments, you're thinking about that last assignment, you're even thinking about how can I use this tool that is statement logic in my day-to-day life, you can account for probability by sticking it right into the translation itself. Okay, second oddity about implication statements. They can connect completely unrelated statements or events. So look, if Carl is teaching logic, then the moon is made of chicken wings. What do those two things have to do with each other? Nothing. Nothing at all, right? They don't mean It doesn't mean anything. The fact that I'm teaching logic right now doesn't tell us anything about what the moon's made of. It doesn't make the moon be made of anything. It doesn't make it true that it's made of chicken wings, right? They're just two completely unrelated things. Statement logic itself doesn't really care about it. All we're looking at with the operator here is what things we can connect together. So look, different statement. If Carl is teaching logic, then the moon is spherical. Well, that implication statement's true because both of those things are true. They still don't have anything to do with each other. But that doesn't matter. That's not something statement logic is really concerned about. On its own, it's just this system, this tool for stitching things together in a certain way and examining truth relations between them. Third, implication statements with false antecedents are also always true. We saw that when we were looking at the truth table. So look, if humans never existed, then the universe would have 12 dimensions. Now, humans do exist. So it's just false that humans never existed. Because it's false humans never existed, anything can follow from it and the implication statement remains true. Just look at the truth table if that seems confusing. Keep in mind what the implication statement is really committed to is just saying that if the first thing is true, then the second would have to be true as well. So if we have something that is false, if something that just never could be true or would be true, right? Potentially even like contradiction or something, you can put it as the antecedent. Then anything can follow. You can have a true implication statement from anything. But that really only works as a matter of pure logic. Because the implication statement is just defined the way it is on the truth table, really just saying if the first thing's true, then the second thing will be true, and if the first thing is false, then, well, it doesn't matter, right? As long as the first thing is false, as long as the antecedent is false, the statement is true. That's really, you get some of these strange results just from the fact that you can view formal logic, statement logic, as this sort of pure thing that we study for its own sake. When we're interested in actually arguing about the world, we want to use this as a tool to translate and analyze arguments to help us construct good arguments. Then what you can actually do is determine whether or not the implication statement is true by appealing to what the world's like. So look, if humans never existed, then the universe would have 12 dimensions. Whether or not humans ever existed doesn't seem to have any sort of relationship to how many dimensions the universe has. Right? Think about the previous example. If Carl is teaching logic, then the moon is made of chicken wings. Whether or not the moon is made of chicken wings is just nothing at all to do with whether or not Carl's teaching logic. Right? They're just unrelated things. So as a matter of fact, in the world we live in, whether or not I teach logic has no bearing on whether or not the moon is made of chicken wings. So if we're presented the implication statement, right? If Carl's teaching logic, then the moon is made of chicken wings. If that's being presented in an argument as a statement about what the world is like and how things relate to each other in the world, then we can reject the implication statement itself because of, I hate to say it, what it implies. Right? Because we can look at that, we can say, look, no, it's just, we don't have that kind of relationship between those things. And so the way we represent the implication statement on the truth table actually shows us that we shouldn't be doing that kind of translation. We shouldn't be putting it that way, right? Or rather, we shouldn't accept such a way of putting it as true. Okay, let's, just before we move on, let's go back to our Word document just to quickly show how we can make the implication table for the sake of consistency. So same thing, we need 3 columns, 5 rows because we need the header row. I'll go ahead and center everything. We've got, oh, it didn't center it, okay. P, Q, if P, and so this is if P then Q. And that's what I was just talking about. So just to do that again, P dash dash by the plus sign. And then down, there's sort of a question mark, and then one to the left of the question mark, you hold shift and press it. It's also the key with period. You get the little arrow. The little arrow looks like that on its own. Word will automatically convert it. And then even if you just produce something like that, you put a little arrow or a couple of arrows down like that with the lines, we'll know what you mean when we're looking at the grade. Okay, so we've got, and we'll center that, make it all bold. So we've got P, Q, if P then Q. And of course we've got true, true, false, false. got true, false, true, false. When we look over here, still want to center this. We look over on that last column, we've got if P then Q. If P then Q is only false if P is true and Q is false. Because really all it's saying is that if P is true, Q has to be false. I know it just sounds like I keep saying the same thing, but this is what I mean when I say this is just sort of a basic kind of cognitive function humans have. I don't know how else to say it. If you can't make that sort of connection between if this and then that, we could use a few other words to try to iterate it, but there's just something almost basic about being able to see that this thing somehow relates to that thing. This goes to here. So it's P, if P then Q is only false, if P is true and Q is false. In the first row, they're both true, so it's true. The second row is that one that shows us what we want, right? P is true and Q is false, so it's just not the case here that if P is Q, then Q has to be true. So it's false. And then in the last two, P is false, and whenever the antecedent is false, the statement's always true. It seems weird, but that's just because the statement is just talking about the case when P is true. It's really just saying it's not the case that P can be true while Q is false. Really all it's trying to tell us. Okay, let's take a look at our fifth and final operator, the biconditional. The biconditional claims that either both logical units are true or false. This gets expressed in English by expressions like if and only if, or as long as, or you'll often see it written this way, if, right, IFF, typically in italics. And it gets represented the way we're going to represent it with this double arrow. So arrows either way. And you can represent that same sort of way, you know, type in on the keyboard shift and hit the comma button, get that little left arrow, put in a couple dashes, put in the right one. Depending on the program you're using, it might automatically convert it, and if it doesn't, it still looks about right. So here's the truth table for the biconditional. Biconditional, like the other three operators we just looked at, also connects two logical units. They don't really have special names, so you've got conjuncts, disjuncts, antecedent, and consequent. And then for the biconditional, well, you can still use antecedent and consequent, but there's just not the same sort of agreed upon language for the biconditional. So I'm just not going to introduce any. It doesn't really matter. It just connects any two logical units, simple statements or complex statements. So here again, we just have the final column. Now, as stated right at the top, what the biconditional is saying, if the biconditional is true, then both of the logical units it connects are either true or false, right? But they're true or false together. That's really the difference. So as you can see in the column for the biconditional, you know, P biconditional Q, it's really saying, look, P if and only if Q. What does that mean? P is true if and only if Q is true, right? So what that means is you can't have one be true without the other. Because it's really just saying, right, the one is true if and only if the other's true, and vice versa. P is only true as long as Q is true. Well, that's true when they're both true. When one is true and the other one's false, it's false. But then in the last row, they're both false. So it could still be true, right? Because it's not really telling us anything about the case where one of the biconditionals is false. It's just saying if one's true, the other has to be true as well. And it works both ways. So it's kind of like a souped up implication statement. The implication statement is trying to just have a unidirectional meaning to it. It's just saying if the first thing's true, the second thing will have to be true. The biconditional is saying either they're both true or neither is true. With the implication statement, right, the consequent can be true whether or not the antecedent is true. It just can't be the case the antecedent is true or the consequent is false. As long as they're both true or both false or just the consequent is true, the implication statement is true. For the biconditional, they're both true or they're both false, right? You can't have one or the other. It's just, right, both together or neither. Now, the biconditional is, in some sense, a little bit simpler than the implication statement, just because it has this relationship that says they're both true or they're both false, right? And you can actually make a biconditional by using some of the other operators. We'll take a look at that in chapter 4. The the biconditional does capture the way we think about some things. So like, Joe is a bachelor if he is an unmarried male, right? Joe is a bachelor if and only if he is an unmarried male. Joe's a bachelor as long as he is an unmarried male. Well, look, we've got P and Q. Joe's a bachelor, Joe's an unmarried male. Now, if we think about the truth table, well, look, if Joe's a bachelor, then he's an unmarried male. And if he's an unmarried male, then he's a bachelor, right? It works both ways. It's really like two implication statements. So it can't be the case that he's a bachelor, but he's married. That would be, well, okay, maybe, let me back up. Just look at the truth table, right? We've got our P and our Q. Let's just go down each row. First row, Joe is a bachelor and Joe is married, right? Well, if both of those are the case, then it's true that he's a bachelor as long as he's an unmarried male. Or Joe's a bachelor if and only if he's an unmarried male, saying he's both or he's neither, right? Well, if he's both, then it's true. The second row, right? Joe is a bachelor, but it's not true Joe is an unmarried male. But that's not what we were saying when we were asserting the biconditional. So the biconditional is false when the one thing's true but the other isn't. The next row, it's false that Joe is a bachelor, but it's true that Joe is an unmarried male. If that were the case, then it just wouldn't be true that Joe is either both a bachelor and unmarried male, or he's neither a bachelor and an unmarried male, right? Neither nor. The if and only if is saying if one's true, the other has to be true. So if we have a situation like in row 3 where one is false and the other one's true, then the biconditional statement itself is false. The fourth row, right? Joe isn't a bachelor, but he also isn't an unmarried male. What does that mean? It's false that Joe is a bachelor, and it's true that Joe is married, right? Well, that's, yeah. When you think about what it means to be a bachelor, it means to be an unmarried male. So if you have a married male, you don't have a bachelor on your hands. So in the case where they're both false, right? It's false that Joe is a bachelor. It's also false that he's unmarried, which we can restate by just saying he is married. Then it's true that Joe is a bachelor as long as he's an unmarried male. We're saying those things come as a package. They're both true or they're both false. And it can be true when they're both false that if one's true, the other one has to be true as well. So biconditionals are useful for capturing that sort of relationship, that sort of necessary relationship that holds between two statements or two logical units. So look, that really takes us to our conclusion of looking at the logical operators. So we've got those 5. I hope that wasn't too quick. Like I said earlier, you might want to watch this video more than once. I certainly recommend reading the text. I go through some of these issues in more detail, so this video lecture really captures the key points that you need to keep in mind. If you have more questions or some of the points don't seem to make full sense yet, definitely I suggest read the text. If you're still confused, rewatch the video. If you're still confused, I suggest reread the text. But you can always reach out to me if something doesn't make sense. Now, I warn you, the first thing I'm probably going to do if you email me and say, I don't quite understand how, say, the implication operator works, probably the first thing I'm going to do is to ask you if you read the text or just send you some of the text. So the way I'm explaining it here in the video and the way I explain it in the written text, those are really the 2 ways that I can think to explain it as clearly as possible. So if you write me a question, I'm likely to email you back with some snippets of the text anyway. So I highly recommend reading the text to start with. Now, I'm not trying to discourage you from contacting me. By all means, if something doesn't make sense, please do contact me. Or if you've got any questions about how any of this works or anything I've said in the text or anything I said in the video, I'm happy to try to answer as best I can. I'm just trying to give you fair warning that if you give me a written question, my written response is probably going to be effectively what I've already put in the text. Part of why I'm writing the text is that I'm trying to put things as clearly and carefully as I can. And so the text is really a result of me thinking about these things over time and trying to articulate as best I can in writing how to explain some of these concepts. I certainly hope that the accompanying video lecture has helped with that. Oh, and I just remembered, I feel a little bit goofy, I still haven't made the table in Word for the biconditional. We can do that very quickly now. So we've got P, we've got Q, we've got P. Oh, look at that. It's not going to do what I want. Q. Now that's kind of ugly. I'm not really a big fan of that. Another way to put in the right operators, if you go up and you pull on symbols, you can insert the right kind of thing, and you can copy and paste if you need to. Oh, goodness. All right, I'm just going to delete those. You might have to dig through your symbols to find the right ones, but once you have them, it should remember them. And of course, we've got, center this, true, true, false, false, because that's just how two simple statements work. And then if we've got a biconditional, if one simple statement's true, the other one has to be true. So in the first line, we get that. They're both true, so it's true. In the last line, they're both false, so it's true. It's only in the second and third rows we have one simple statement being true while the other one's false. The biconditional is trying to say precisely that can't be the case. It can't be the case that one is true and the other isn't. So in the second and third rows, it too is false. All right. So with that, that is, I believe, all I have to say here. I hope this has helped clarify some things. As I said, chapter 4, we're going to take a look at the use of brackets and how to actually make complex statements that themselves have other complex statements as part of the units. So how to sort of build with these. So what we've been looking at in this chapter is really how to take each of these operators and apply it in its simplest form. So negation applies to one thing. All four other operators apply to two things. We're just applying them to simple statements for the sake of clarity. So negation, it just negates a simple statement. A conjunction, disjunction, implication, or biconditional somehow connects two simple statements together. Next chapter, we're going to see how we can connect not just simple statements, but complex statements, and how we can string things together to make them larger and larger by introducing more and more operators. So try to get a good handle on the material in this chapter. Try to be in a position that you have a pretty good sense of what operators are, how they work, what their truth conditions are, before moving on to the next chapter, because the next chapter is going to make things a little bit more complicated. But the benefit to making it more complicated is that we're going to be better able to translate from natural language into statement logic, and that's going to help us use the tools of statement logic to analyze arguments for validity and invalidity. Okay, I hope this has all been as clear as possible. I'll actually stop now instead of just repeating myself and going in circles. So please feel free to contact me if you've got any questions or if any of the material remains unclear after looking at the video and looking at the text. And I hope you're all doing very well. So I'll have another video posted next Monday. I'll try to get it up more in time for class. I'm sorry this one was much later in the day. I'm still trying to adjust to this, my new scheduling reality in light of recent events. So I hope you're well, and I'll see you next week. Bye for now.